Hello again. Welcome to the second lecture on Module 2. We've already gone through the introduction to constant coefficient differential equations. We spoke about linear and dependence and independence. We've talked about fundamental solutions, the Wronskian, the homogeneous and non-homogeneous differential equations, initial conditions, initial value problems, boundary value problems, verifying solutions of given differential equations, and the superposition principle. For this lecture, we'll be talking about the first method of solving constant coefficient differential equations before we introduce you to the characteristic equations. This lecture is about reduction of order. And for the sake of simplicity, I'll be talking about a second order differential equation. Assuming that my differential equation is of the form a2 of x, y double prime, plus a1 of x, y prime of x, plus a naught y equal to 0. So as you notice, we're looking at a second order general differential equation and not necessarily with constant coefficients. Now, we assume that if we had one of the solutions of this differential equation given to us, I'm going to call it y1 of x, it turns out that I could assume that my second solution here will be some product of some function u of x multiplied by my original solution, which is y1 of x. And this is the second solution of that differential equation you can achieve. Now, we could actually prove this by substituting this back into my differential equation and actually derive the formula for a second solution given the first solution. But that is already typed up on my lecture notes that's been uploaded. So I'm only going to give you the formula. So given one of the solutions of a second order differential equation, you could always use the reduction of order formula that, again, you could derive, known as y2 of x is y1 of x multiplied by the integral of the following expression, guys. E to the minus the integral of p of x dx divided by the square of the first solution dx. And that's how you could find the second solution. Again, you could start with star. You could take appropriate derivatives of this. You could substitute it back in the original differential equation given, and you could derive this formula yourself. And again, the derivation is on my lecture notes provided for you on Canvas. I'm here only giving you the formula because I just want to go through the motion of actually doing an example for you. So let's start with an example so you could actually see how this is illustrated and how it's going to get worked out. I'm going to be looking at my example 19 from the lecture notes. I'm looking at the differential equation x squared y double prime minus 3x y prime plus 4y equal to 0. And again, you notice this is not necessarily a constant coefficient differential equations, even though once this section is finished, the rest of the section will primarily focus on constant coefficient differential equations. So for this example, given this differential equation, and given that I know one of my solutions, or my first fundamental solution is y1 is equal to x squared, I've been asked to find the second solution of this differential equation using the reduction of order formula, which is right above it. So let's see if we can go through the motion of doing this. My second solution is going to be my first solution, which is x squared times the integral of the square of my first solution in the denominator, so it'll be x squared squared, which is x to the fourth. And in the numerator, I will have to find my p of x. Now remember that p of x could only be achieved or could only be detected once the differential equation is written in standard form. So to find the p of x, I'm going to grab my differential equation here, and I'm going to divide everything by the leading coefficient and per se write it in standard form. So I will have y double prime minus 3 over x y prime plus 4 over x squared y equal to 0. Now here you can clearly see that my p of x is negative 3 over x. So therefore, if I go back to my formula, I'll have e to the minus the integral of p of x dx, which is negative 3 over x dx and dx for the actual integral, which doesn't seem to be a difficult integral to solve. Continuing our work, I have x squared on the outside. My numerator becomes e to the integral of dx over x with the 3 being pulled out. And I'm going to have my x to the 4th in the denominator. Here I have x squared, the integral of e to the 3. The integral of dx over x is the ln of x, and you don't need to worry about the constant here. Divide by x to the 4th dx. Some algebra here. I'm going to move the 3 up to the power of x. So I'll have e ln of x cubed divide by x to the 4th dx. Natural log and exponential functions are inverse operations, so they will be canceling each other out. So this will turn into x squared. The integral of e to the ln of x cubed will just be x cubed. Divide by x to the 4th dx. Now this becomes x squared. The integral of 1 over x dx, which becomes x squared natural log of x. And this becomes my second solution. So if I were to write the general solution, it's my second solution. And now, at this point, since I was given the first solution and I just figured out the second solution, now using the superposition principle, assuming that these are fundamental solutions, not assuming, we know, we can comfortably say, therefore, my general solution will be c1 y1 plus c2 second y. Now, again, we know y1, which was a quadratic, was an x squared. So it would be c1 x squared plus c2, my new function, which is x squared ln of x. And here is the solution to the given differential equation, guys. Ah, that's funny. I can just do that. There we go. So there are a few more examples that I'll work through for you guys to look at and practice. And given that this is quite of a short and simple section, this will do it for us. I'll see you guys on the next session.